So, Professor Marc Henry, can we talk a little bit about energy, spin, free energy, internal energy within the context of entropy?
So, that's a very technical question.
It's very technical.
I'm not sure that everybody will be interested in this kind of topic.
Let's try.
Let's try. I will begin with the most simple or the most complex concept, which is energy. Energy is simultaneously simple and complex. It's simple because when you say energy to the layman, he will not be surprised. Say, oh, energy, okay, because you have gasoline, you have electricity, you have nuclear energy. So he will seem comfortable with this concept because it's everywhere in the media, but he will never really think what is energy. Because if you really try to think what is energy, you have a big problem. Because it is not. It was Poincaré which gives the right definition of energy. It's something that I cannot define, except if I take an example. That is to say, if I try to define energy like this, I cannot explain what it is. But if I speak you about electrical energy, now I can speak about energy, because I have a word which is electrical, which means that is a certain kind of energy, and this kind of energy comes from what we call electrons, which are moving in a conductor with a potential difference, because I am speaking of electrical energy. If I remove electrical, energy becomes nothing. So we are with this strange situation where we use a concept which cannot be defined. Or if we want to define it, we need an example, because we cannot define it in a general way. And it's not very satisfying from an intellectual viewpoint. If we use concept, we want that this concept should be easily defined in a few words. With energy, it's not possible. And there is another way where we can see that that energy is not there. We cannot get real definition, because there are some people who are very clever. Say, wow, energy is the sum of electrical energy, mechanical energy, thermal energy, optical energy. They will give you a list of all the examples, and some plus, you get a number, and they call this number total energy. The sum of all the kind of energy. But now we gave you an example that it is useless. You go to the 18th century, and you will ask this question, the same question, let me define what is energy. You will have a list, and then you will miss in this list, you will not have nuclear energy. Because at that time it was not known. So you could not put in energy nuclear, because this concept was nonsense. But if you ask the same question 2 centuries after, of course, you will not forget to add nuclear energy, because you know that it exists. But now I will let's move 2 centuries after our time. That is to say, in 2000 and 200. Are we sure that the list we make today will be the same in 2 centuries? We don't know. And as we don't know which will be the least, we cannot know what is energy. Because if you need to define a thing but a list, as soon as you forget one form of energy, you are out. You do not define the concept. And this is the trouble with energy, that we cannot define it precisely. And this is very strange because we cannot define this concept and we use it everywhere. Energy, 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 we cannot define. We can even go to Aristotle, because Aristotle as a word was energeia. Energeia. It looks like energy. In fact, it is the semantic root of the word. It came from the Greek, energeia. But what was energeia for Aristotle? It was a potentiality. That is to say, something which could exist, which does not exist, but which could manifest. Sometimes, somewhere, energeia could give rise as a visible phenomenon. We call it also potentiality. It was, for Aristotle, it was matter as a potential. Very strange, matter as a potential. It is something which is not here, but we can be here. If you wait times, which is time enough, you will get this thing. So you see that energy is very strange. And we use it without realizing, for most of the people or the scientists, that it is an undefinable property. So this is the reason why I prefer to rely on something which is easily defined, which is entropy. Because you have, as I explained a little bit before, if you have several forms of energy, you have a single concept which is entropy. It's much easier to define one thing than a collection of things. So this is the first reason why we should use the word entropy, because it's more easily defined, and then after, it is the volume which is accessible at a certain temperature in space and in velocity. You have two ways of, if you want to speak of natural phenomena, what is its position in space, and as there is time, is the particles that I am considering at rest. Okay, we call the static view, nothing moves, or does this particle have a speed, in which case, which are the interval of speed that I am allowed for the given temperature at which I consider the system. And this is entropy. The larger the possibilities, the larger the entropy. The smaller the possibilities, the smaller the entropy. We have a very nice way of justifying this. It's just to take, for instance, the three common states of matter, solid, liquid, and gas. What is the difference? We say that solid has a lower entropy than liquid, and that liquid has a lower entropy than gas. If we take the definition I just take, we can understand why. Because when you take a solid, you have a certain amount of volume, of space-time, and this doesn't change. For instance, could you give me your pen? Yeah. The object is here, the solid, so it is not here. The molecules which are making this pen stay at this position, not at this one. And as they cannot go there, the volume that they can occupy is smaller than the whole volume of the room. And that's why we say it is a small entropy, because we cannot go everywhere in the room. Now, if you take the glass of water, now this is a liquid. What you see is that the liquid will occupy a whole volume. Yeah, it would be fine that I have a glass. It would be much here what is the difference? Is that this is as a shape, because the velocities of the molecule are very small. And so they cannot go, they are doomed to stay in this volume. Here what I see is that the volume is much more, the accessible volume is much more important, because the liquid fill holds, there is no space between the
container
and the liquid. So we see that here the molecules can go everywhere in the liquid, and they have a speed enough not to stay always at the same time. This is why there are a larger entropy here. And now if I evaporate this glass, because if I wait, all this liquid will become a vapor, a gas, and the molecules can occupy every position in this room, not outside because there is a glass and the walls, but every system here will be accessible to this water molecule, and now the entropy will be very, very much bigger. So we see that the entropies can be clearly defined, amount of possibilities of moving in space and time, how I can go. And he can explain, we can readily explain why there are solid, liquid, and gas. We cannot do that with energy, because energy, we just have to make a list, and we are never sure that we have not forget something. Here I'm sure that nothing has been forgotten, because you have, say, position and speed, we know all the possibilities. So we know the function entropy.
Yeah.
And this is the reason why we should always use entropy and not energy. Another example is when we have light here. Okay, it's very nice to have light, but I know that in a few days I will receive a paper from the society which give me electricity, which say, you have consumed this amount of energy. And as you have consumed this amount of energy, you should pay me this amount of money. This is called the facture d'électricité. Electricity invoice. That's right? Okay. You get an invoice. And they say that you have consumed energy. It is for your energy consumption. And now I say, wait a minute, guys. The first principle of thermodynamics states that energy can be never created nor destroyed. So it doesn't have consumed anything. The energy was there before I switch on the light, the same energy was there. I have consumed nothing. This is the first principle of thermodynamics. And they send me an invoice telling me that I have consumed energy. That's crazy. In fact, you have to do something. Because if you have to get money, to give money, it's because you have a benefit of using. If you have not consumed energy, you have transformed it. It was given you as electricity, and you have transformed this as light or as heat if you want to have warm. But this is not consumption. This is transformation. You have transformed. So you should have an invoice for the transformation of energy. Or if you prefer, because as we don't know what is energy, you can have an invoice for entropy production. Because you have produced entropy. And as you have produced entropy, you have to pay. Because as soon as you produce entropy, this is the basic law of nature, you should pay. So you see, even in our common day life, we are crazy. Because we state that there are principles, first law of thermodynamics, and we send papers to people violating this principle. So the most correct way of putting things would be to get invoice for entropy production. What is the problem? Just a system of words. But by saying entropy production, I told the reality. By saying energy consumption, this is not reality, this is a dream. So, another reason for sticking to entropy, not to energy. Then after, that become very comic. Because we don't want to speak of entropy because we say energy consumption. And we have to say entropy production. And we don't want to say this. But now, what happens when you say internal energy or free energy? Here we can, it's very comic. Because if you translate the word free energy, that means énergie libre. Why I have to pay for something which is free? So this is not a good word. Because in fact, free energy is entropy. This is a déguisement. Or we say this in English, masquerading. You have a concept, and you masquerade this concept because you don't want to say the word. So you invent a new word, free energy, to say that you are speaking of entropy, but not of energy, because it's not really energy, it's entropy. In fact, what is free energy? It's entropy at constant temperature and pressure. That is to say, I fix the temperature and the pressure, and then I let the system evolve. And when I see that it evolves spontaneously, I say that the free energy has changed and has been minimized. But I can say that no, the free energy has not decreased, the entropy has increased. That you say, I don't need a new word. I just take the entropy and explain that at the only difference when I speak about an entropy production, it is at constant temperature and pressure. Because I can make the same entropy production at constant volume and entropy. And this we would call internal energy. If I made it at constant pressure, constant entropy, it will be called enthalpy. And if I make it there, I put the condition in the definition of the word. And it is always the same concept, entropy production, which has changed. It is the condition that I fix for making the study. This makes nonsense. Why should I put the condition of measurement in the concept I want to define? The concept can be defined whatever way I choose for measuring.
So what has been so difficult in the history of physics to accept entropy?
What has been difficult is that the first thing that was discovered, the first concept that was for instance, we start from Galilei. Galilei has shown that in the sky, when you take a telescope and when you look at Jupiter, instead of seeing one point, with the eyes, when you look at Jupiter, you see how many points of light? One. When you take the telescope, what you see, this is not 1 point, but it is 5 points. 1 point which is very bright, very big, and teeny point which are moving around. This was the key observation that you say, when you look at a given time, the points doesn't move, they are fixed. But if you make the same observation 1 day later, and if you have noted the position yesterday, today you will see that the teeny spot will be another place. That means that they have moved. The spot have moved. In 1 day, they have changed their position, so there is a speed. And that was the very beginning of the mechanical revolution, where it was, we have to explain we have a central point, Jupiter. We have the teeny spot, which are satellites. Why the satellites doesn't fall on Jupiter? Because what we know is that if you take two masses, they attract each other. And this was the genius of Newton. Maybe it's a false story, but this is like this in the books. He was under an apple tree and he was resting, and boom, an apple fall from the tree, and of course, as soon as they fall, it becomes, eat up the ground. And bingo. The satellites of Jupiter are attracted by Jupiter, like the apple, which is attracted by the Earth. But what happened that was shown by Galilei, the points are not steady. They are moving, and they were moving in circles or ellipses. But when you compute the forces, you see that there is one force which is oriented towards Jupiter, but as they are moving around an ellipse, you have another force which is called centrifugal force, which oppose. Because the movement, we have an opposing force, that means that the two equilibrate and they always get the same trajectory. So Newton put up equations. It is the third law of Newton's, which was able to explain the whole structure of the cosmos. But there was still a problem. This force of attraction between the mass, what it is. Because between the 2 points, Jupiter and the satellite, there is vacuum, nothing. How a force can be exerted as there is nothing? This was very strange. Because this was what he calls an action at distance. There was no material contact. Through the vacuum, mass attract. Very strange. If you explain this, I would be very interested. Very difficult to explain what is the mechanism. So, what was done is to forget the force, because we cannot see this force. It's very difficult to understand. What we will make is stating from a physical principle, which is the energy of the system is constant. Never change. That is to say, if I look at this concept that we call today energy at one time, I will get exactly the same number at any time. This number cannot change with time. We recognize the first principle of thermodynamics. Energy can never be destroyed nor created. You give it at a given time, it's always the same. And from this, you derive Newton equations. As soon as you say the energy cannot change, you have a mathematical derivation which tells you should have the third law of movement of Newton. No more forces. No more problem with two masses which attract each other. You just have energy which is conserved. And the consequence is Newton equation. And so this was very soonly discovered. It was the first thing that was discovered and would give rise to what is called mechanics, the science of mechanics. Energy, mechanical energy, is always conserved in any kind of movement. So I can predict the trajectories by just stating that there is kinetic energy, potential energy, and I can, when I lose kinetic energy, it becomes potential energy. When I lose potential energy, it becomes chemical energy. It's the picture of the pendulum. When you look at a pendulum, you look, when the pendulum goes at the point, highest point in space, its speed is 0. you have no kinetic energy. So all the energy is potential. Now you take the vertical. Now you see that it is the potential energy which is zero, but the kinetic energy is maximum. It is the point where the speed is the fastest. And then you go back again at a point where you still have no kinetic energy. Again, only potential. Potential, kinetic, potential, kinetic, potential, kinetic, potential, and this never stops. This is called oscillation and shows how the energy is always conserved and can be expressed as movement or non-movement. And this was again, it was Galileo which studies the movement of the pendulum. So you see, behind the notion of energy, there are very old experiments, because Galileo, it's 4 centuries ago. And at that time, there was no even a single reference to something like entropy. Everything was energy. Kinetic, potential, I can transform, but it was always energy. And then came the work, it was at the first quarter of the 19th century, came Sadi Carnot. Sadi Carnot says, oh, we have thermal engine, because this was in the 18th century where the steam engine were invented for making work. That is to say, instead of using horses or men, we can use machine. And then we know how a thermal engine works. You have to put coal or gas, and then you have a machine which burns the coal, create water vapor, and this water vapor create pressure, which allows a metallic piece move, and this compresses the steam. So the heat is again, you change the temperature to remove the piston, and so on. You make a cycle. And Sadi Carnot was showing that if you compute the amount of energy you put under the form of coal, and you compute the energy that you can get for moving, you lose something. And this thing which is lose, it was no name, but Carnot was the first to point out that you cannot transform energy with 100% efficiency. There is always a loss of energy. And then came Clausius, Rudolf Clausius, which at the beginning, just in 1850, told, wow, this loss of energy is entropy production. He coined the word entropy for this loss of energy. And here you came at the critical point, that entropy at the very beginning was defined as an energy loss. And if you remember what I told you a few minutes ago, I told you that energy cannot be defined. So you try to define entropy with a concept, a loss of something that cannot be defined. It's crazy. And that's the reason why the notion of entropy was clearly not understandable, because first it's very hard to define energy, and then you begin to speak of energy loss. Typical. And we have to wait Ludwig Boltzmann, we have perceived the difficulty with entropy view as an energy loss. He said entropy should be more something which can be defined more easily than energy. And he came on his famous equations, Boltzmann equation, where entropy was, as I explained to you, the amount of volumes that you can occupy in space and in velocities. He came to this definition, which is very clear and which doesn't refer to energy, and which allows, as there is a single entropy, there is no trouble with, there is no potential entropy, no kinetic entropy. That doesn't mean you have just entropy. And so the entropy concept was birth. His birth was associated to a loss. And what happens when you associate a definition with a loss? The human mind is not happy because we have lost something. It will be a much better way to define entropy as a gain.
You think this is basically has happened because it was not clear at this time?
It was not clear what was energy at that time. Nobody knows what was energy. As I told you, the energy concept was forged because from the mechanical, the equation of Newton's, the equation of Newton was clear. If you want to justify the equation of Newton, the energy cannot be changed. Because as soon as the energy changes, you cannot have the Newton equation. So from mechanics without friction, mechanics without friction, because if you have friction, it doesn't work. But for mechanical systems where there is no friction, you know that to explain the law of motion, you can say, instead of invoking force acting at distance between mass, which are crazy, you just have to say there is a thing called energy which never changes. And so what they try to do with thermodynamics, as with mechanical energy, it was clear. You just have to say that energy is conserved. They were saying, for instance, that when you have friction, energy is no more conserved. That's true. But they say, oh, it's not energy which is not conserved. It is mechanical energy. They say there is another kind of energy, which is thermal energy. Because there was, when you have friction, you have heat. And they say, okay, you lose mechanical energy, but you gain thermal energy, friction. And when you make the sum, it does not change. And then after, they go to electricity. There are the laws of electrical circuits. And they see, oh, in an electrical circuit, you have another form of energy. So they say, oh, mechanical energy can also give electricity. And then mechanical energy can also be expressed as nuclear energy. Then there was chemical reactions, explosion. Explosion is energy. And so they came to the idea that the energy is never conserved. And in order to keep the conservation, we sum all the different kinds of energy to get a constant. But as I stressed before, this is not a definition. This is just a recipe. Take all the kind. If you invent another form of energy, you have to change your recipe. This is not acceptable from a scientific viewpoint. But it was accepted as the first law of thermodynamics. And this is the main reason why entropy is poorly understood, because it is always associated to energy, which is not definable. So entropy is no more definable if you link it to energy. And it is also associated to a loss. Something that you could have, but that nature takes to you. A tax. But tax. People don't like taxes. And as they don't like taxes, we will forget such a concept and focus of energy, which is maybe not definable, but we can speak about the different transformation of energy in different forms. We can speak about that. And here you have the reason, because if entropy would have been discovered before energy, it would be much simpler.
Mm-hmm. But it's even actually worse, because the first principle of thermodynamics says energy is heat and mechanical work, and both has been given the same unit, joule. Heat and energy has been nominated with joule.
Yes, because that was a trick.
So it's not coherent at all.
No, it's not coherent, but this is a trick. Prestidigitation. What is entropy? It's energy, joule per Kelvin.
Yes.
So if you, as soon as you multiply entropy by a temperature, you get energy. They call this thermal energy. But this is fictive.
But there's a confusion that thermal energy is not the same like heat. Is not the same like heat, because there's this misunderstanding that heat is energy.
The culprit was joule. Why we have chosen the energy joule, the unit joule for energy? Because we have a culprit, which is James Prescott Joule. James Prescott Joule was not a scientist. He was making beer. Making beer. It was his job. And for those who doesn't know, but I can tell you that when you are making beer, what you need, if you want to have always the same beer, you need a constant temperature. The fermentation process should be done at a constant temperature, because if the temperature is not constant, your beer will be awful. So Joule, who was making beer, has invented the most accurate thermometers, because it was critical for the beer to have very accurate thermometers. And even in the physics laboratory, they have thermometers, but they were much less accurate than that of Joule. And so what Joule has made, he made very clever experiment where he shows that if I drop a weight in gravity, this is mechanical energy, the drop of a weight, he make a rope. The weight was connected with, which is here where my English becomes limited, a pulley. Pulley, it's the rope pass on something which can turn. And this pulley was moving in water, the pale. Again, I don't know the English word for pale.
Spinning?
What?
Spinning?
Paddles?
Spinning.
Wait, spin paddles.
He was turning.
That is, you have the weight which falls,
Yeah.
and the paddle which turns because it is connected to the weight which is falling.
Right.
And then you have a thermometer in the water.
Okay.
And he calculates the amount of mechanical energy that was given to the paddles by dropping the weight. This is very clear. It's a product of the mass by the gravity. You get the force, and by the displacement, you get the energy. And then by the thermometer, he was recording the change in temperature. And as he has very accurate thermometers, he was able to detect teeny change of temperature. That was not possible in laboratories because they have not thermometer which was accurate enough. But Joule could make this. And what he shows, that he knows the specific heat of water, and if you know the specific heat of water, which is entropy, we don't call it entropy, we call specific heat. You see, again, very strange, because you call this entropy. And if we know the temperature variation, by multiplying the heat capacity by the variation in temperature, you get the same number as the one that you compute by following the weight. And he was the first to realize that mechanical energy has been dissipated as heat. And there was a one-to-one correspondence. The same number was obtained by heating as by following the weight. The idea was, if I have an entropy change and I multiply by temperature, I get an energy, a new form of energy that will be called thermal energy. And as we want that energy is conserved, we will sum with all the other form of energy. We have a new form that we will add in order to keep the principle, the first principle, alive. You see and Joule made experiments in water, in oil, in mercury, and he shows that whatever the substance, of course, if you change the water for oil, you not have the same temperature change. But as you don't have the same heat capacity, the product of the heat capacity by the temperature is always the same. And the idea that we are allowed to add in all the forms of energy we know, a new one which was linked to entropy variation, with an advantage that we do not no more need of speaking about entropy. Because as we multiply by temperature, we get energy. And so we can make entropy aside. It exists, but we don't speak of the word. We speak instead of energy, of friction, of thermal energy. And here we are in very bad shape. Because you cannot make this addition. It's like, why we cannot make this addition? Because mechanical energy can allow you to do work. But with heat, when you have friction, you have increased the temperature of the matter, but this increase has been made in every direction in terms of movement. You say, I cannot get a coherent movement from this second term, from entropy variation, I cannot get a direction of the movement. It always goes anywhere with the same probability in any direction. And so you are not allowed to sum up these two forms. It's like if you say, I have carrots and potatoes.
Until Boltzmann. Until Boltzmann.
Yeah. And I say, I will add the number of carrots and the number of potatoes to get the number of vegetables. It's crazy. You cannot do that. Because even if you add carrots and potatoes, vegetables is not a concept. It's not a real thing. It's a category. You sum up, you get a category, but you are still carrots and potatoes. And so that was what has been done. And the only justification for such a masquerading is to not have to speak about entropy. Everybody speaks about energy. But what has been shown by Prigogine, and if you take the equation, multiplying by the temperature, you are not allowed to do that. Because if you want to make the multiplication, the temperature should be constant.
Now,
let me finish. You have an entropy change. You want to get an energy. You say, I multiply by temperature. But what you have to realize, that to be allowed to make the multiplication, the temperature should be the same before and after. Because if the temperature has changed, you are no more allowed to make the product. And in fact, when you look at a biological system, if I measure the temperature in your body, it's 37 degrees. If I measure outside, it's not. So I cannot make this trick because the temperature is the same. And so this is the reason why it's better, much better to say you have mechanics where energy is conserved, but this is just a fairy tale, this conservation energy, because we take the precaution to remove friction. If we release the constraint of frictions, the energy is not conserved.
Do you think that the first principle of thermodynamics finally has complicated to understand biological systems?
Yeah. It not and only it has complicated the whole field of physics and thermodynamics, because when there is no first principle, there is just one law, it is the second law. Entropy of the universe should never decrease. And when you say this, if you are at constant temperature, you can translate this sentence, entropy of the universe should always increase. You can translate this in a decrease of free energy, a decrease of internal energy, if a decrease of enthalpy, as soon as you state what is kept constant during the transformation. Temperature, pressure, volume. But this is not fundamental what you are. It's technical. And the energy appears as soon as you are interested in technical application. If you want to stay at the fundamental level of comprehension, there is one concept which is entropy. And there is one law, single one, not two, nor three, one law which states that entropy of the universe, it's very important, universe, it's stated in the paper, entropy in the universe should never decrease. And then, of course, in what you have entropy, you multiply by temperature, you can speak of energy if you wish. But this is not mandatory. You are perfectly allowed, that was the real foreseeing of Prigogine, that the real variable of evolution is entropy, not energy. So every biologist, every chemist, every politician should think in terms of entropy, not in terms of energy. The only guys which are allowed to speak about energy and forget entropy are the guys which fix two parameters, volume, pressure, temperature, volume, temperature, pressure. If you make this restriction, then you can speak in terms of energy. And of course, they have forged new words, free energy, internal energy, enthalpy, for speaking of entropy under different conditions. But this is technical. This is not fundamental. All the thermodynamics can be rewritten. I've done that in this paper. I have written all the thermodynamics by removing completely the energy concept, become secondary, technical, and stressing the importance of just a single concept, which is entropy, which should be defined at the beginning. There is a function named entropy, which measures the amount of volume and speed that I can access at a given temperature. And if this quantity is known at a given time, I know that in the future it has to be increased if computed on the whole universe. Not locally, as Schrödinger has done, but on the whole universe, it will always augment, increase. And this is a very nice explanation for me because we have cosmology, which has proven that there was a Big Bang and the universe was in expansion. But they say that the universe is expansion, but they never say why. Me, I can add, the universe is impatient because entropy cannot be destroyed. And as it is always created by every processes postulate that there is an increase in entropy, we have to have the container of entropy which should change. Mm-hmm. Mm-hmm. And we call the container of entropy, we call this universe. And the thing becomes very logical and clear. We can make a link with cosmology, the Big Bang, and the second law. For me, it's a perfect demonstration of the usefulness of the concept.
So it looks like historically seen, between 1850 and 91, I think, when Boltzmann published his work, there the road has been prepared for a new understanding of the world and the universe. Because from there then until Heisenberg, quantum mechanics has been developed. So that was basically at the very beginning, these 50 years, triggered a major shift in our perception of the world.
Yeah. But that's always the same problem, that when you say you are the citizen of the universe, for your ego, you're too small. Because the universe is so big. It's better to say we are the citizen of the earth, because our ego is much larger comparable to the earth than to the universe. So we have a psychological problem here. We want to be important, and so we prefer to take the reference of the earth rather than the universe. But in fact, the real reference, the good one, is the universe, not the earth. The earth is a subsystem of the universe.
Can you talk a little bit about the spin?
Yes, so we have spoken about energy and entropy. And sometimes we encounter another entity which is called spin, or more technically, angular momentum. It's the same as spin. So here the reason is very clear, in fact, that we have in nature 6 universal constants. The first one, which was discovered, was the gravitational constant of Newton. By stating that 2 masses attract each other, there is a constant, which is called the gravitational equation. And when you take this constant, you multiply by the mass of the Earth, and you divide by the square of the radius of the Earth, you get what is called the acceleration of gravity. 9.8 meters per square second. It is the constant of our Earth. But this constant is linked to the gravitational equation of Newton, to the mass of the Earth and its radius. Hello, Gupinette. I have my friend which has come. She wants to eat. Well, she will just look at us. I will give it food later on. So, that was the very first constant which was discovered. The second one was the speed of light. You say when light was investigated, we understand that a ray of light was traveling at 300,000 kilometers per second. This is the second universal constant. Then there was the electrical charge of Coulomb. For electricity, we have the quantum of charge, which is 1.6 10 to the minus 19 Coulomb. Then there are the Avogadro numbers, the number of molecules in 1 mole of matter. Then we have the Boltzmann constant, which is an entropy, Joule per Kelvin, which was discovered at the same time by Max Planck, when Max Planck was studying the black body spectrum, he had to compute the value of the Boltzmann constant that was introduced by Boltzmann but not computed. Planck makes the computation. And then you have to add a sixth constant, which is the Planck constant. And here we find spin. Because the Planck constant, this unit, is mass times an area times the frequency. This is the unit. There is no name for this unit. It's a unit. It's if you want to take a unit, it can be joule, which is energy, times a time, joule second. But there is no name. And this was the first apparition of angular momentum. And this angular momentum was well known in mechanics. It appears as soon as a particle is rotating around another one. You can define what we call an angular momentum. What was new is that, of course, when there was the discovery that the model of Bohr, that you have electrons which are moving around protons in an hydrogen atom, of course they have an angular momentum. It's called orbital because there is a particle which is going around another one. But what was discovered is that there was another momentum, angular momentum, which was not orbital, but due to the rotation of the electron on itself. And this has been called spin. And when quantum mechanics was developed, at the very beginning, this spin was not very interesting. It was just a new contribution that you have to add. And nobody was seeing its real understanding. We know that we need this spin, this additional spin, but it was not very clear why we should have this kind of spin to add, except that when you look at the solar system, everybody understands that the Earth is rotating around the Sun and rotating around itself. So if this is for the solar system, why not for the atom? That was the idea. Okay, so this variable was introduced, but there is really a problem with this additional spin, is that the first kind of spin was in quantum physics, you can use an integer, 1, 2, 3, 4 units of the Planck constant, and everything was fine. But when you want to introduce a second contribution, here we have a trouble because it was not 1, 2, 3, or 4. It was 1/2, 3/2, 5/2. That is to say, there was half spin. And this was very strange, that when the spin was considered, you have to consider either integer values and half values. This was not understandable. Mm-hmm. Until the 30s, where an English mathematician, which was called Paul Dirac, was saying, we should understand why it should be 1/2 and not 1, as for the orbital contribution. And then he realized that this was the consequences of relativity. In relativity, you cannot separate space and time. And it was the same in quantum mechanics, in fact. You are not allowed to separate space and time. So that means that the second contribution, which was a contribution which divided by 2, relative to the orbital contribution, which is an integer, this was the consequences of the 4D structure of space-time. I will not get into the mathematical details, but it was very clear that it was associated to the fourth dimension, which is the time. And then came one fundamental point of quantum physics is that matter doesn't exist. And here we have a problem. Because if matter doesn't exist, light does not exist neither. So how we can distinguish between light and matter, which are basically the two forms that we can see in the universe. Either you have materials particles of matters, either you have ray of light. And as you know, particles have not the same, does not obey the same equation as the ray of light. Particles obey the equation of Newton's, ray of light obey to the equation of Maxwell. So you cannot say that it's the same thing because it's not the same law of motion. And here it was the key that the spin was making the link, in fact. That is, when you have half values, you are speaking about matter. When you take integer values, you are speaking about light. That is to say, instead of looking at the mass, you look at the spin of a particle, because in quantum physics, everything is particles. And so you have to decide if this particle is a particle of matter or a particle of light. And the idea was very clear, the mathematical consequence was very clear. If you get half value, you have to be matter. What we call matter, that is to say, we cannot cross. If you are integer value, you are light, or more precisely radiation, because you have a form of radiation that are not light, but you are radiation wave, if you prefer. And this is very clear. So the spin allows you, when you have only particles and you are at a relativistic level, where space and time mix, you cannot no more use mass because you have the Einstein equation. Energy is mass times the square of the speed of light. So mass disappears at this level. And you cannot measure mass. All you have is energy. But you always have spin. And by looking at measuring spin, you know if you have a particle of matter or a particle of light.
How do you measure the spin?
Oh, it's very easy. You get magnetic fields. You take the particles and you put in a magnetic field. And in a magnetic field, if there is no magnetic field, the levels of energy are all the same. But if you now make a magnetic field which is not zero, you will get as many levels as the spin. The rule is very simple. If you have a spin which is S, you will get 2 times S plus 1 states. So let's take an example. I take a set of particles, what we call a jet. You send this jet into a magnet, and if you get 2 jets from one, after crossing the magnetic field, you say we have spin 1/2. Because 2 times 1/2 plus 1 equal 2. Because you see 2 jets from one jet, that you say the spin is 1/2. If you get 3 jets from one jet, the spin is 1. Because 2 times 1 plus 1 equals 3. If you get 4 jets, the spin is 3/2. If you get 5 jets, the spin is again integer, it's 2. If you get 7/2, 6, no, 9, no, 6. We say that the spin is 5/2 and so on. So you take a jet of particle, And by the number of subjects you get with the magnetic field, you get the spin.
Why is this spin of importance?
It is important because when you realize that the Planck constant is a spin, this gives a very deep meaning to the Planck constant. It's a unit of spin. That is to say, basically, if the Boltzmann constant is an entropy, Planck constant is a spin. So this is important because what quantum physics apply to the spin, not to the energy. Because the quantum of action is a spin, it's not an energy. So this is why energy completely disappears in this kind of level. You see, when you have the sixth constant of physics, the first one is gravitation, fundamental. The second one is the speed, fundamental. The third one is an electrical charge, fundamental. The fourth one is the number of mole, the number of molecules in one mole, fundamental. The five is Boltzmann constant, it's an entropy. Entropy is fundamental. The sixth one is the spin. The spin is fundamental. When I say gravitation, speed, charge, number of molecules, number of atoms, entropy or spin, I have never spoken of energy. This means that energy is clearly a secondary concept. It's not a fundamental one, because there is no universal constant associated to an energy. And this is clear because, as I told before, energy cannot be defined. So it has nothing to do in the picture of this universal constant because it cannot be defined. Entropy can be defined, so there is a constant of entropy which is Boltzmann constant. This makes sense. We put in the sixth universal constant of the universe the things that could be defined. You could be defined what is gravitation. It is the curvature of space-time. That was the interpretation of Einstein. You can define what is the speed. It is the amount of space in the unit of time. You can speak about electrical charge. This gives to electricity and magnetism. You can say what is the mole. It's the number of molecules in the volume of matter. You can clearly state what is entropy. And you clearly state what is spin. You don't need to speak about energy, or if you prefer, if you want to use energy, you are not a scientist, you are a technician. That is to say, you use a secondary concept, which can be derived from the sixth fundamental one, and if you use a secondary concept, you are making technology. Energy is important for making machine, for making device, but this is not a fundamental quantity. Entropy has its own constant, so it is a fundamental concept. And in fact, it is the most fundamental of the six, because, as I showed in Prigogine, behind entropy you have life, information. So if you want to make a hierarchy, surely I will put the quantum of entropy at the top.